We already know how to solve probability problems that involve rolling two dice. We've done a lot of that. So let's take an example like that and go a little further with it. Suppose we've got an event and call it E, and the event is that the sum is 5 when you roll two dice. And the question is, what is the probability of that event? In other words, what is the probability of getting a sum of 5 when we roll two dice? As you know, one of the easier ways to picture the sample space is to put it into a 6x6 square. So you can see there are 36 equally likely results in the sample space. And if we're looking for a sum of 5, it's also easy to see in this format that there are 4 possibilities, either 4, 1, 3, 2, 2, 3, or 1, 4. So by the basic probability principle, that probability is simply the number of things you're looking for, which is a sum of 5 divided by the number of elements in the sample space, which is 4 over 36, and of course that reduces to 1/9. So this is old hat. We've done this. I want to take it a little further. What if I told you that I've already peaked? I haven't shown you the roll yet, but I've already peaked, and the sum of the dice is odd. Does that matter? Does that change your perception or reality of what the probability of getting a sum of 5 is if you know for sure that the sum is odd? Let's investigate that a little. I'm looking for, and I'll write it in this sort of just written out notation right now, the probability of that event E, given that I know that the sum is odd. Now what does that imply about the sample space? If I know that the sum is odd, the sample space doesn't consist of things like 1, 3 anymore, because 1 plus 3 is 4. That's even. There are lots of elements of the sample space now that are out the window because I know that they can't happen anymore if I know that the sum is odd. And as a matter of fact, half of the sample space is gone because half of the sums are odd and half are even. So looking at it from that point of view, the number of things that I want, which is getting a sum of 5, didn't change. There's still 4 things. 4, 1, 3, 2, 2, 3, and 1, 4 are, of course, odd, so that doesn't change. But the number of elements in the sample space now has been reduced by half. Instead of 36, there's only 18 odd sums. And as I said, the numerator didn't change. There's still 4 that sum to 5. So the probability of getting a sum of 5 given that the sum is odd is 4/18, which reduces to 2/9. So the earlier question was, does it matter that I know that the sum is odd? And the answer is obviously yes, because the probability in general of getting a sum of 5 is 1/9. But if I know in advance that the sum is odd, the probability is actually doubled to 2/9. And that leads to something we call conditional probability. If you have a probability that includes an extra condition, something that's thrown in extra, here it was that the sum was odd. We knew that the sum was odd. That probability is called a conditional probability. And we've got a special notation. Going back to that example, I wrote it before just sort of in words. The probability of E given that the sum is odd. It's the number of elements in the sample space with conditions in the denominator. In the numerator, it's whatever happened to what I wanted, incorporating the condition, and that came out to be, of course, 2/9. Suppose we call that condition that given the sum is odd F, then we're going to here be saying that F is the condition that the sum is odd. In other words, it's another event. E is the event that the sum is 5. F is an additional event, which is the condition, and that is that the sum is odd. And given that, we write the probability like this. There's a vertical bar there, a vertical line in between the two events. It's read as the probability of event E given event F, or if you want to say this in more words, it's the probability the event E occurred given that the event F occurred. It's the probability of E given F. When you read that conditional probability, I said it, but I'll point it out, that vertical line is always read as the phrase given that. Also, you don't have to use E's and F's. We could just say that in our particular example, we could write the probability that the sum is 5 given that the sum is odd. Instead of writing E vertical line F, we could just write it out in words, the probability that the sum is 5 given that the sum is odd. So that's what we mean by conditional probability, and that's the notation for conditional probability. Venn diagrams are very powerful in a lot of things that we do, and in particular, it's very powerful in looking at conditional probability. So I want to look at this in terms of Venn diagrams. If I've got two events, E and F, E intersect F is that blended area in the middle where the two events overlap. The event E is the whole blue circle, including the blended part, and F is the entire red circle, including that blended part. That's just a typical Venn diagram. You're used to seeing those. I want to apply that here. So what if I'm looking at the probability of an event E given F? In other words, the probability that E occurs given that F occurred. If I look at it this way, the event that comes to the right of the vertical line is the event that's already occurred. So in this case, when I say the probability of E given F, I mean F has already occurred. So if F has already occurred, I don't have to consider anything outside of F. So if it helps you, you can just sort of picture the circle E just going away. However, I did leave the intersecting part. It's really not blended anymore, but this is the intersected part. I left that. With equally likely sample spaces, which is what we're considering here, if you want to calculate the probability of something, you take the number of ways you can get it over the number of elements in the sample space. Here that translates into being the number of elements in that blended area over the number of elements in the entire circle. We know F occurred, so the whole sample space now is the circle F. So the probability of E given F is the number of elements in the overlap of the two circles divided by the number of elements in the circle representing the event that's given, the thing that's already occurred. So the probability of E given F is simply the blended area over the number of elements in the circle F. Conversely, if I wanted to do it the other way around and I wanted to look at the probability of F given E, now I'm saying that the event E has already occurred. Well, if the event E has already occurred, I don't need to consider anything outside of the set E. So I could just forget about the circle F. And now I'm back in the same game, except that I'm looking at the set E as being my entire sample space. So again, the probability of getting F, if I'm going to get F, is going to have to come from here because the rest of the circle F got eliminated, over the number of elements in the sample space, which has been reduced to E. The condition reduced the sample space to just E. So I hope you can see how the Venn diagrams make it pretty clear why this works the way it does. To summarize, the probability of E given F is the number of elements in the intersection of E and F divided by the number of elements in F, and it reverses itself when you're doing the probability of F given E. That's still the number of elements in the intersection of E and F, but it's divided by the number of elements in E. So again, the denominator always draws from the given that set. So if you want to know what goes down here, you always look at the given that. So whatever goes down here, you're looking at the given that. The numerator is always the overlap. Technically, I derived this result for equally likely sample spaces. I won't go back through the derivation, but I will say occasionally you do have to work with sample spaces that aren't equally likely, and if you do, you can still do it. You just have to look at it in terms of probabilities instead of counting. If you're counting up things that aren't equally likely, it doesn't work anymore. So essentially, if you can convert to the different form if you're not doing equally likely just by changing all the n's to p's, and you get the other result. We seldom have use for that directly because almost all of our sample spaces are equally likely. So most of the time, we'll be using that first variation of the formula. It turns out, though, if you really understand how this, for the lack of a better term, this given that condition, how that restricts the original sample space, most of the time you can solve these conditional probability problems without even formally using any formula. And I'll show you what I mean by that. Suppose I have this problem. If two cards are drawn without replacement from an ordinary deck of cards, what is the probability that the second card is a heart, given that the first card was a heart? First of all, let's translate that into our conditional probability. The given that part goes here to the right of the vertical line, and the thing we're trying to find the probability of goes here. So the probability that the second card is a heart, given that the first one is a heart. And I'm covering up that formula entirely because I'm trying to make the point that you really don't have to have it if you understand what the idea is behind conditional probability. This condition means something has already occurred, and what's occurred here is that the first card was actually a heart. So that reduces or restricts our sample space. So if we know that the first card was a heart and it was drawn without replacement, then instead of there being 52 cards in the deck, after that first draw, there are only 51 cards in the deck, and the one that got drawn out is the one that got reduced. There's still 13 clubs, 13 spades, and 13 diamonds, but now there are only 12 hearts, because that's the one that got drawn out. The heart was drawn out. So given that restriction on the sample space, what's the probability you get a heart the second time, assuming you didn't put the card back in the deck after you looked at it? Well, it's pretty simple. You count the number of hearts, what you're looking for. You're always doing the probability of what you want, a heart. Well, there are only 12 hearts now because you drew one out and didn't put it back. And since you didn't put it back, instead of there being 52 cards in the deck, there's only 51 cards in the deck. So the probability that the second card is a heart, given that the first is a heart, or was a heart, is 12 over 51. Now we'll give you a little bit of a word of warning. You need to reduce these fractions, and lots of people think 51 is prime, but just need to remember this. 51 is not prime, and it comes up quite a bit. Just remember that it's not. It's actually 17 times 3. So at 12/51 can actually be reduced to 4/17. So don't do all the hard work and then forget to reduce your fraction or think you reduced it when you really didn't. So the probability the second card's a heart if the first one was a heart is 4/17. Simple example, conditional probability, where you really don't have to use the formula we derived if you understand what's going on, and that's really what you can do most of the time. Let's do another problem. This time we've got a container with 35 green marbles, 20 blue marbles, and 4 red marbles. Notice 35 plus 20 plus 4 is 59. So there are 59 marbles in that container. Two of those marbles are randomly selected without replacement. We're going to let E be the event that a green marble selected first, and we're going to let F be the event that the second marble is not green, which means it could either be blue or red. And we want to find the probability of F given E. Now, although that's presented that way with the letters a lot of times, my real preference is to write it out in words. I think it's less likely you're going to get it backwards or get it wrong if you just write it out. So instead of writing F given E, I'm going to actually write out what F is, which is F is the event that the second marble is not green. I just write that out. And E is the event that the first one was green. So my recommendation is, most of the time anyway, to write these things out in words. In any case, now that you've written it out, you look at the condition that's already occurred. E is what's already happened. You already know that the first one was green. So if you look at it from that point of view, if you know the first one was green, there started out being 59 marbles, 35 green, 20 blue, and 4 red. But if you know the first one was green, then instead of having 35 marbles that are green, you now only have 34 that are green. The number of blue and red stayed the same, which means you have only 58 marbles left. So what's the probability that the second one's not green? Well, remember, not green can either be blue or red. So there are 24 of those. And like I said, there are 58 marbles left because you drew one out. So the probability the second marble is not green given the first one was green is 24 over 58. Again, that simplifies because they're both even, and 29 is prime, so you end up with 12 over 29. So I hope you're beginning to see how this flows, and you don't really have to use those formulas if you understand what you're doing with conditional probabilities. Let's try another one. This one said this graph has stats about distracted drivers below the age of 40 who were involved in fatal crashes. If a driver is selected from the under age 20 group, what is the probability of the accident being related to cell phone use? And then round your final answer to 3 decimal places. The thing you got to understand here is it's giving you information about three different age groups, the under age 20, the 20 to 29, and the 30 to 39 age group. And they're asking us about, if we know that the driver came from the under 20 age group, then what's the probability of the accident being related to a cell phone? So that's the conditional probabilities. You have to recognize that. That's the probability that the driver came from the under 20 group, and then we want to know the probability that that accident was related to the cell phone use. So that's here. So you have to get accustomed to reading these problems and writing them as these probabilities, in this case as a conditional probability. So you know that the person's under the under 20 age group because it says they were. The driver is selected from that under 20 age group. So what the condition does here now, what the restriction is that you're only looking at the under age 20 group. In other words, these don't even matter anymore. That's the restricted sample space now. So instead of looking at everybody, you're only looking at this under age 20 group, and if you take 515 and add 140, they're going to be 655 total drivers that are under age 20. So what's happened is you've reduced your sample space now to just the 655 drivers that are under age 20. Once you do that, you can see, well, what is if you know that they're under age 20, you know you're going to only be dealing with that 655 people. And then you want to know the probability it's related to cell phone use. Well, the cell phone distraction is the red. So that's the 140. So out of the 655 total people, you only have 140 whose accidents were caused by being distracted by a cell phone. So again, it's a conditional probability. You drew your information from a graph, but it's the same idea. And it said to write your answer to rounded to 3 decimal places, and that's 0.214. I hope you see how this flows now. The basic thing is to first find out what your sample space changed to after the restriction or after the condition.